Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is day 2 of the Puzzle Advent Calendar as found by matthewscroggs.co.uk, his website. And so this problem was very interesting to me, and I went to bed trying to think out a solution to this, and I came up with an algorithm I feel so smart about I didn't even have to look it up. I don't know, I'm just so proud of myself. I'm gushing for myself here. That this was, for me, being a computer science student, this was actually a little challenge to try to think outside the box, because I could write a program that could solve this problem, except for the solution to this problem might take, I don't even know how long. Would it be a day? Would it be a week? Could it be 10 years? I don't know how long it would take to do. Maybe I'm exaggerating a little bit, but it will definitely take a long time to solve this if you just blindly go ahead and just brute force this thing. So here is the problem. There's a lot going on here. I guarantee you that. Let me clear this out. And so the problem is the number 7 times some number n has 37 factors. And remember, of course, a factor is a value that divides into a number. So like the number 6, as you know, if you remember from day 1, if you were following along on day 1, the factors of 6, at least for this example, are 1, 2, 3, and 6. Numbers that divide into the number, other numbers that divide into the number that divide evenly. And so in this case, there's going to be some number that has 37 factors. And the one other thing you have to account for, since it's 7n, that not only does the value of the number have to have 37 factors, the number, basically one of the factors, one of the divisors has to be the number 7. And so the problem here is find some ginormous number that has 37 factors that's also divisible by 7, figure out n, and then basically work out 8n, and then figure out how many factors that number has. And you're like, oh my god, that sounds complicated. And it is. This problem took me a while to kind of formulate and go with it. Because first off, you're like, how do I even figure out how many factors any number has, let alone anything, let alone specific, cases. So this function here I wrote, and this takes into account everything I'm just saying, and it actually implements this algorithm right here that I looked up, because 24 hours ago I wasn't even thinking anything about this stuff, and this is very interesting stuff when it comes to figuring out factorizations and stuff like that. So we're trying to find the prime factorization, and in the process we can figure out all of the number of factors. So what this code does is takes a value, finds its prime factorization. So the number 108 is 2 times 2 times 3 times 3 times 3. Those are all prime factors. And then it does a little extra jiggery pokery, and then from there figures out the total number of factors. So it basically, start with your number and divide by 2. And if you can divide by 2 equally, then you have a factor. And then cut that number down by that factor, and then just keep going. Try to divide by 2 as much as you can, and then try to divide by 3 as much as you can, and then try to divide by 4 as much as you can, and so forth and so on, until the number reduces down to 1, because then there's no other factors for you to worry about. And since every number 1 and above is going to have at least one factor according to our rules, I start with the total number of factors being 1, and we start working from there. And then start dividing by 2, and so forth and so on. So you can look through this code. This is integer division for those of you who are not familiar with what that is looking like. But the interesting part here is that, like, at the end of the day, where you're like, okay, 108 is 2 squared times 3 cubed. And you're like, well, how do I get the answer from that? And the answer is you take the number for each of the different values, like 2 and 3. You take the powers, you add 1 to each individual power, and you multiply them all together. So for 108, there's 2 2's, so we multiply 3 by, and there's 3 3's, we multiply the 3 from over here by the 4. So 3 times 4 gets me 12. There's 12 total factors of 108. And again, I don't 100% understand the reasoning behind that. I just found the algorithm. A lot of times I wish, instead of just giving me the algorithm, maybe there is something somewhere about oh boy, nope, about, where I can find this algorithm. How do you prove this? Like, it's great to just have something written down here on a web page somewhere, but I don't 100% believe in it, because I need to see a proof, more than just to trust me on this. That's what mathematicians do. They definitely don't trust anything more than what they can prove. And sometimes you have to take things at face value, but this is not one of them. So this algorithm does exactly that. For any number, it does this formula, and it figures out the number of factors from that, and so I don't have to necessarily worry about that. So again, the tricky part was, and again, this is a speed up from the way you could do it if all you did was go ahead and try to divide by 2, and try to divide by 3, and try to divide by 4, and try, and just kind of work your way through how many factors do I have. That's going to be much slower than what you see here. So just trust me on that. This is a faster way of doing things, and I could speed this up even more by if I had a list of all the prime numbers, instead of just increasing by 1 every time. And I was working that too, but at the end of the day, the numbers that we're going to be generating, unless you want to generate millions of prime numbers, which takes a ton of time in its own right, then you really can't rely on that methodology. Or you have a list of prime numbers somewhere that you could put into memory or from a file, or something you generated previously, then there's really no reason to worry about any of that kind of stuff. So using this function, we just go ahead and start working our way. And again, the fun of this is that, yeah, what is the number? The number's a 31-digit number. And so how long is it going to take you? And actually, if you do this in C++, like, what data structure are you going to use to create a 31-digit number? Like, I don't think that works I don't think you can do a 31-digit number as a long or a long or anything like that. You would have to use crazy number libraries, which, like big integer or whatever, those kind of libraries. But Python has all of this, arbitrary integer sizing. That just comes with the language for free. You don't even have to think about it. That's one of the fun parts of Python. And especially with the IntelliSense and Visual Studio code here, I'm liking Python more and more every day. I mean, of course, obviously, everybody in the world is on board with that, but I don't work in Python every day, and I have never done so. So for me, working through this has been a joy. So now you're like, well, okay, if I can just start from 2 and work my way up, how long will it take to generate to figure out a 31-digit number? And you're like, well, okay, that's going to take a long time. It's going to take a long time. So the question is, how can I game this? And gaming is in quotes. Like, knowing what I know about mathematics and knowing what I know about what I'm staring at right here, how can I reduce down this problem into a reasonable amount of time? And as you will see when I run this, it takes about a second, no more than a second to generate the answer. Otherwise, how long would it take? Again, I don't know the answer. Days, months, weeks, years? I don't know how long it would take if we just brute force this thing. But coming back to this, we are saying that there's 37 factors. So just think about working your way backwards from this algorithm. So if there were 108, how did I get the 108? It was this squared times this squared, plus 1, of course, right? So 2 squared plus or times 3 cubed. So 3 times 4 got me the 12 for 108. I'm sorry if I said 108 factors or whatever. I meant 12 factors of 108. So the thing is, because I said the value here is the number is 37 factors. And if I'm adding 1, like, what gets me 37? So if I have 37 factors, some number times some number times some number times some number, an arbitrary number of numbers multiplied together need to get me to 31 or 37. Sorry, 37's prime. Try to figure out a factor of 37 that's not 1 and not 37. You're not going to find it. So what that means is there's only going to be one. There's 37 factors, but they're all going to be powers of something, because I can only get there by basically if some number came up 36 times, and I added 1 to that, and that was the only factor, I would get 37. There's no other way to get 37 factors. So it's going to be something to the 36th power will get me there. That's the only way I can, and that's so you can see here. This is n to the 36th power. That's a huge number, huge number. So, you know, think about what's 2 to the 36th power. 1 to the 36th power is 1. 2 to the 36th power. Well, 2 to the 32nd power is 4 billion. So 8 billion, 16 billion, so 64 billion. And that's just entry. That's 2 is 64 billion. Imagine 3 and 4 and 5. These numbers are absolutely ginormous. There's no way you would solve this brute forcing it unless you you worked smarter and not harder. And so the other rule of thumb was that whatever we are working with has to be, you know, on top of it being a power of 36, has to be divisible by 7 so that I can work my way back and get an integer value for my n. So basically, n has to start at 7. And it turns out to be the answer is 7 to the 36th power. And then we can work our way back to, you know, so to divide back and figure this out. So let me run the program and you'll see what let me get rid of my trying. But maybe you saw it running when I had things going that, yeah, this is the only solution that I know of. And if you know a better way, or if something in here is wrong and you know it, please let me know, because again, I am a computer scientist and I am just learning this as I go. But the best way to learn is to try to teach the stuff that you're trying to learn. So what do I get when I run this program? Let me get rid of this nonsense. And there we go. Those are my numbers. And I only have 10 seconds to copy this thing. Oh, actually, and it's going to keep trying to find answers to this problem, but essentially this is the only solution. You know, so that number, wherever it went, has 37 factors. Where did it go? There we go. Oh my God, come on. Just help me a little. Oh my God, just help me a little bit. Nope, not gonna do it. Okay, visual. I gave you cred, and now you're screwing with me. Okay, so let me just there we go. Put that number in here. So I believe it's a 31-digit number for both of these. So this number has 37 factors. It's the smallest number that has 37 factors and is also divisible by 7. So if I take this, divide by 7, and then multiply it by 8, so I can get the 8n, this is the number I get. Holy crap, yeah, that's a big number. And when I say how many factors does that number have, running it through the same algorithm as before, I get the answer of 144. And so I understand that other people get different problems, because on my computer here when I'm working, and on my phone when I was like trying to fall asleep and not doing anything, and just trying to fall asleep and couldn't fall asleep thinking of this problem, I looked it up on my phone and I got a different problem. So, but this is the general rule here. This is generally what I'm thinking of here. And so thanks for sticking it out with me. This was a lot of fun. If this is problem 2, I'm freaking out about what problem 3 is going to be for me. But I hope to learn from this. And thank you, Mr. Matthew Groggs, for coming up with all of these problems. I believe he has 100, 200, 300 problems on his website. And one more coming in 7 hours and 42 minutes for me. Thanks for sticking it out with me, guys. Have a great day. Please comment if you need to, or if I did something totally wrong. And I'll see you in the next video, wherever that is, whenever that is. Take care, everyone.